We good to start?
And so, yeah, welcome to Computational Mathematics Part 2. And our first speakers are Natalie Heath and Rachel Kuhl. So, right ahead.
Hi, my name is Natalie Heath, and my partner is Rachel Kuhl, and we created this project in spring 2020 as part of a computational problem-solving course. This program was made in Wolfram Mathematica and allows a user to solve and create tangram dissection puzzles.
So first, I'll give a little bit of background on tangrams. Some of you might recognize them from math classes in elementary and middle school. But tangrams is a puzzle that consists of a set of 7 standard shapes, which you can see at the right. And these shapes come together to form a square, but then they can be rearranged to make various other designs. It's notable that all of the angles in each of these shapes are multiples of 45 degrees.
So I'm going to go ahead and start out with the first half of our project with a demo. So upon first running the program, you'll be presented with the screen, and I'm going to show you the first half, which is design. So when I click choose design, I'm redirected to a gallery of all the puzzles here. You see we've made a few tests down here, but let's say I wanted to try out the rabbit. So once I click on the rabbit, I'll be redirected to this solving screen, which appears with the outline in the background and all the shapes necessary to solve it kind of scattered around the screen. So I'm going to go ahead and start solving it, but you can see at the right, there's a few different buttons. There's buttons for rotating, which will rotate either clockwise or counterclockwise. And there's also a button for flip. You can flip any of the shapes, but this is really necessary for the parallelogram because for these triangles and the square, you can reach any position by flipping or by rotating, except for the parallelogram because it's not symmetrical. So let's say that I wanted to get a little crafty and I wasn't really sure what the solution was. And I just wanted to fill in as much space as possible without actually trying to solve it. So that looks close enough to me. So I'm going to go ahead and try and finish that. And it's going to tell me that my solution is not quite correct. And it'll give me the option to either keep trying or to give up and go back to home. But I'm not going to quit her. So I'm going to keep trying. It is a little easy for me since I designed it, but few more shapes here. Try to get the margins as close as possible. It's hard to be exactly perfect. Good. And there we go. Congratulations. You solved the tangram puzzle. Would you like to browse other puzzles? And if I click OK, it'll take me back to the gallery, or if I hit cancel, I'll go back to home.
So for our puzzle formatting, throughout our code, we use 3 main global variables. The first is all puzzles, and each puzzle is a polygon. And the second is puzzle strings, which contains the name for each puzzle. And those names are displayed on the buttons in the gallery that you could see during Natalie's demo. And then the last global variable is puzzle shape list, which contains the list of shapes that are needed to solve each puzzle. The first puzzle in all puzzles is named by the first string in puzzle strings, and it's solved using the first list of shapes in puzzle shape list. This is the same for the second puzzle, third puzzle, and so on. In each of the shape lists for each puzzle, each piece in that shape list contains its own element called a shape info. And each shape info consists of 3 parts. The first part consists of the shape's vertices, and those vertices are formatted as if the origin were the center of the shape. The second part of the shape info is the shape's actual center, and the third part is the shape's angle of rotation. The angle of rotation is updated using the rotate clockwise and counterclockwise buttons that you saw on the solve screen. And each time one of those buttons is pressed, 45 degrees is either added or subtracted from the angle of rotation. The second element, which like I said, is the actual center of the shape, is updating using locators and a locator pane, which Natalie will now explain.
So if you saw the shapes when I was performing the demo, you might have noticed that each one of them had a little crosshair in the middle, and that's representative of Mathematica's locator function. For our code, the main runner of that display was a locator pane, and a locator pane takes 2 main parameters, one of which is a list of locators, which we dedicated each shape as its own individual locator. And the second parameter is a dynamically updating background, which means that as we move things around, it updates in real time, so everything looks real fluid. For this, each shape had its own locator, like I said, so that we could move them independently of the other ones. We also needed to keep track of which shape was currently selected, so that if we clicked rotate or flip, it would only rotate one particular shape instead of all of them at once. This was done with the help of some stack exchange code, which essentially finds the locator that was closest to the last mouse click, and then sets that to a value that we can then manipulate and use it to say, rotate this square or rotate this triangle.
Another way that you can move the shapes, in addition to the drag and drop technique, is by rotating them and flipping them. So because our vertices, the ones that make up the first part of the shape info, are formatted as if they were centered around the origin, no translations are necessary to make these two operations work. And as I mentioned before, the buttons on the solve screen are what cause the change in the angle of rotation. And then the formula that we use for our actual rotation function is there on the screen. And in this formula, xy is the original coordinate, which is like one of the vertices of a shape. And the point to the right of the arrow is the rotated coordinate. And in the rotated coordinate, d represents the distance from the original point to the origin. Theta represents the angle that the vector from the origin to the original point, what the angle that vector makes with the x-axis. And then theta prime is the angle that the shape is to be rotated, which is denoted by the angle of rotation in the shape's shape info. And then our flip button reflects the shape across the y-axis, and it does this by multiplying the x-coordinates of each vertice of the selected shape by a value of -1, and it also multiplies the angle of rotation by -1.
So in order to get the actual shapes from that shape info that Rachel just talked about, to like with the vertices, the center, and the angle of rotation, we used a function we named toGraphics. This is located in the background portion of the locator pane, and since it's updated dynamically, it allows us to update the centers of the shapes as we move them around the screen. It also updates the vertices so that they're rotated properly based on whatever the current angle of rotation is. And it translates them from being centered around origin to being centered around their actual center on the locator pane. This also preps the shape for its actual display, taking it from just a bunch of numbers to the actual triangles and other shapes you saw. This is actually a section of our code, and if I were to add a graphics here in the front, you'd see an orange triangle with an opacity of 0.75.
So when Natalie clicked the finish button on the solve screen in the demo that you saw earlier, that is a button that prompts our program to determine whether or not you have actually solved the puzzle that you're working on. And the criteria for solving a puzzle is that you have at least 96% of the background filled in. And we settled on 96% because the area of the background that remains uncovered must be less than the area of the smallest piece in the puzzle. And the minimum value for the smallest piece's area is just over 5% of the total area of the puzzle. And we find this overlap percent using a region intersection, which takes the portion where two different regions overlap. And so in this region intersection, our first region is just the puzzle itself because it's already a polygon as is. And then the second region was a little bit more difficult to find because it consists of all of our pieces, which are, of course, disjointed shapes. So to make those disjointed pieces into a single region, we look at each piece as a polygon, and then we use region union, which is a built-in function in Mathematica. And we use that function to unify all of those polygons into one region. And after that, we find the area of the region intersection of those two regions. So once again, the background and then all of the shapes put together. And then we divide that by the total area of the puzzle. This gets us the percentage of the puzzle that you have filled in. And if what you have filled in ends up being at least 96% of the total area, then you'll get that congratulations box at the bottom. But if not, you'll be prompted to keep trying.
So now I'm going to demo the second big half of our program, which is actually making your own tangrams. So if we go back to the home screen here and click on the Create Your Own box, it'll redirect us to this grid here. And as I start clicking points on the grid, you'll start to see this red line appear. And as I get to 3 or more points, you'll see this blue outline of a shape. And this shape, this blue here, represents the shape that you're actually going to be making. So if you can see on the grid that it's made up of 45-degree angle triangles. And we made it this way so that it kind of mimics the original Tangram set. And if I tried to click a point that didn't form a line of either 1, -1, 0, or undefined with the previously clicked point, let's say like here, it will not allow me to do so. It'll only allow you to click along the lines. So this also comes with a lot of restrictions, and there are a few ways to get an invalid shape, one of which is to create a shape with a side that is not following the 45-degree angle rule. So if I were to click finish now, it's going to tell me my shape is not complete. I need to check for edges without an outline to ensure that all angles are multiples of 45 degrees. So that's one of the ways to get an invalid finish. And another way is to create a complex shape, which is essentially a shape that crosses over itself at some point. So let's take this hourglass here. If I were to click finish now, it's going to tell me that I cannot have complex shapes, and I need to ensure that there are no lines on my polygon that cross each other. So those are the invalid finishes, but let's create a shape that actually works. Outside of those, you're kind of free to make whatever shape you want. I'm just going to go for a little C shape. Looks good to me. And so when I click finish, since this is a valid shape, it'll take me to this screen, which will ask me if this is the shape I want. And I can either hit yes or no keep working. And no keep working will take me back here. But since I think I'm pretty satisfied with it, I'm going to go ahead and finish. And it'll prompt me to name this. And I'm going to name this one, let's go for Brexit. Give that a second to generate here. And it'll direct me to a screen that is very similar to the one you saw for solving the rabbit. But as you can see, these shapes are definitely not the standard set of tangrams. And we'll talk about that a little bit more, but this is because we had to randomize the types of shapes there are. And I can solve this one just as well as I can with the same buttons. I can rotate these and flip them. And if I go back to home and I go to the gallery, you'll see the rabbit pit is right there, and I can click on them again, and it'll take me back to the screen with the original pieces. So there were two main suggestions kind of thrown around in the beginning when we were trying to tackle the problem of making your own tangrams. The easier method would to be have the user take the standard set of 7 tangram pieces and move them around the screen to create new puzzles. But the problem with that was that the user would know their solution. And so a harder method was to have the user draw an outline of their puzzle and have our program randomize the pieces. Which one did we choose? We chose to randomize them. This is one of our samples that we made that clearly has pieces that are not part of the standard set.
So for our create your own, as you saw in the demo, the user is presented with a 45 degree angle grid. And that grid is on something called a click pane, which is like an interactive interface where the user can click different points like in the pane. And as they click different points, they are added to a point list that helps us draw the outline of the shape that they are trying to design. But as you saw before, not every point that the user clicked is added. The point has to make a slope of either 1, 0, -1, or undefined, which is straight up and down, with the previous point in the point list. And this helps us ensure that the pieces of the puzzle that the user is creating all have angles that are multiples of 45 degrees. And for the finish button, the invalid designs that Natalie showed us were ones with angles that were not all multiples of 45 degrees, as well as complex shapes, an example of which is on the right. And complex shapes are simply shapes whose lines intersect each other. If the user tries to click finish with an invalid design, they'll be prompted to keep working. But if the user does have a valid shape, they can name their puzzle and then solve it. So what happens when the user has a valid shape is that the input of the name prompt box that popped up for them is then added to the global variable that I talked about in the beginning, puzzle strings. And then the polygon that is the puzzle itself is added to the global variable all puzzles. And then once our program splits the puzzle up into the randomized pieces, the return shapelist is added to the global variable puzzle shapelist.
So in order to randomize the pieces, we wanted to make sure that it was as unpredictable as possible. But along with that, we had to set some restrictions. So our first solution was to have a random point appear anywhere within this given polygon, which is represented by the black outline. But a problem with that was if I had a point that was, say, here, I don't know if you can see my cursor or not. If I had a point that was around here and it created a slope of 1, it would create a very, very thin piece right next to the edge of the triangle. And that was something we wanted to avoid. So in order to do that, we created an inner polygon within the outer polygon, which is represented by this black triangle in the middle. And to create that inner polygon, we took the original black outline here and translated it in 4 different directions. And we found the region intersection of each of those 4 translations and the original polygon to get that little inner box in the middle. This just helped us get rid of any super small pieces and still allowed for a bunch of randomization. And here's some of our code that helps us do this. This looks like a lot, but I'll explain. It creates a random point within the inner polygon we defined, and it finds a line with a random point and a random slope, and it'll create a cut line based on that. And it'll find the intersections between that line and the shape. And if there are more than 2 intersections, it's sent to our split by intersections function. And if there are only 2 intersections, it is split by our half region function, which Rachel will explain.
So the first method that we started using for splitting shapes used a half plane and a half region. So what happens here is that we have a cut line, which is that black line going through the parallelogram, which was determined from our splitPiece function. And then we have to find a plane on either side of that cut line. Half planes, they take a direction. So for the red half plane, the direction would be right and up. And so after we find that half plane, we then send it to our half region function, which takes the region intersection of the background polygon and the half plane. And we have to do this twice because, of course, there are 2 half planes, one on either side. So the direction for the blue half plane would be left and down. And we do the same thing with region intersection and that half of the polygon. So after doing this, we would end up with the 2 pieces that are on either side of that split line on the parallelogram. And then those pieces would be added to the shapelist for our puzzle. And we thought that this method was going to work for all of the designs in our code for the Create Your Own. But as we got further along, we realized that it only worked for convex polygons, and we needed to implement something else for concave polygons. So first, just ignore all of the numbered vertices and the stars on that diagram, and just take a look at the cut line and assume that we were going to use our original half-plane approach. So the red star is the random point that we generated within the inner polygon, and then the black line is the cut line. The half plane on the left side of the cut line would return a piece that is just fine, we would be able to use it. But on the right side, the half plane would have returned 2 disjointed polygons, which doesn't make sense for making up a single piece. So what we did was, if our splitPiece function found more than 2 intersections, and the intersections are the white and yellow stars, we focused on only the 2 intersections that surrounded the random point, which once again is the red star. Then we found where those surrounding intersections would be if they were on the edge of the polygon, and the surrounding intersections on this diagram here are the yellow stars. As you can see, the first intersection is that bottom yellow star, and it comes between vertices 3 and 4, and the second comes between vertices 5 and 6. So to get our pieces, after splitting this whole piece, to get the first region, we start at the first intersection, and we draw around the shape in the order that the polygon was drawn until we reach that second intersection. So it goes from the bottom yellow star to vertex 4 to vertex 5 to the top yellow star. Then to get our second region that results from the split, we start at vertex 1 of the entire polygon, and then we travel around the polygon in the direction that it was drawn and we stop at that first intersection. And instead of going on to the vertices that are between the two intersections, we skip straight from the first intersection to the second one. And then once we get to the second one, we continue drawing around the shape until we get to the end of the polygon at vertex 8. So this piece would go from vertex 1 to 2 to 3 to the bottom star, and then it would skip over vertices 4 and 5, and it goes straight to the top yellow star. And then it finishes out the piece going from vertex 6 to 7 to 8. You can see that the two regions that this method would return are the smallest square looking piece at the bottom right, and then the rest of that entire polygon without the top right portion of it being split or disjointed by the cut line. So then we would be able to use these two pieces that actually made sense to be added to our shape list that would be used to solve the puzzle.
Does anyone have any questions?
Suppose your cut line hit it 3 times.
That would only occur if the polygon was convex and it happened to hit like at a corner, I believe. So we took care of that by not allowing convex polygons or
Okay,
complex.
so you can't have this kind of, okay. Okay.
Can you go back to the thing? I think it can occur on some concave polygons. So like if the cut line, okay, so like say this was your random point right here, and the cut line had a slope of 1 and went through vertices 3, 6, and 8. Because it just looks at the two vertices that surround it, it would only end up looking at vertices 3 and 6.
Okay. Any other questions?
How do you regulate the size of the polygons? Like it seems like there's always a couple that are larger and then one that ends up smaller, but I might have missed it, but I don't think that was put into the code. Does it just tend to work out in that way, or did you all account for that?
So the standard set allows for 7 pieces. So that is like the max amount that we allowed for our create your own like methods to split the puzzle up into, so they didn't get to be too small. But that being said, if the polygon or if like the design that the user originally drew had like a small area, then it wouldn't go all the way up to 7 pieces. It would have fewer than that. And the reason for like sometimes like one piece will be like smaller than the rest of them typically, or actually we don't know like the order in which the puzzle splits it up, but we think that those are likely the final piece that the program still has to split. And even though they can get pretty small, we do restrict them from being less than 5% of the total area of the puzzle, which goes back to why we have, like for a criteria for actually solving the puzzle, you have to have at least 96% of the puzzle covered.
To go off of that as well, when we were looking at like the piece list of the randomized shape, we prioritized the bigger shapes that had yet to be split with a weighted value.
So if there were pieces, like it splits the puzzle piece by piece, and so at the beginning the pieces are of course going to be bigger, so they're less splits. So as we continue doing them, like as Natalie said, when we're picking the next piece to split, they have weighted probabilities. So the bigger pieces are more likely to get picked to be split again.
I think it would be fun for you to let children play with this and just make their own puzzles and see if they can solve them.
Yeah. I've definitely spent a lot of time playing around with it. It's pretty fun.
Any other questions for our speakers? Well, let's thank the speakers, and the next talk's in about 5 minutes, 5 or 6 minutes. Okay.
but that's because it's just a regular sine wave. So it's a consistent amplitude and a consistent frequency all the way throughout. It's computer generated. And that's the sine wave that's loaded whenever you start the program to begin with. On the record screen, there's also two other buttons. These buttons are trim and about. If you click on trim, then it's going to give you the screen that appears in the bottom right. There's a big blue play button that allows you to play back the trimmed version of your sample. And there's also two sliders that move a green and red cursor. The green cursor determines the start, the red cursor determines the end of the sample. If you're playing an instrument and you click record, and you have to take your hands away from the keyboard, you have to play the sound on the instrument, and then go back to the computer and hit stop, you're probably going to have a little bit of silence at the beginning and end of the sample, and you don't want that. You don't want to have all that silence floating around whenever you're trying to use it as an instrument. So by trimming the sample, you can use just the portion of it that's musically useful, just the portion that you want. If you click on the About function, it will bring up instead a graph of the fast Fourier transform of that sound, and we'll get into that math in just a moment. But first, I want to talk about the play screen. This is the part where everything comes together. This on-screen keyboard here, it works just like any other keyboard. If you play the lowest C, then it's going to play back your sample without any alteration. And the rest of the keys are that sample pitched progressively higher, going up an octave and a fifth. If you look at all of these sliders up here on top, those are the frequency and amplitude for various, there's 8 oscillators. So these are 8 sine waves that you can use to recreate your function. That's the sample approximation function. But as to the math that goes into all of this, the main mathematical engine for this is an equation called the Fourier transform, or for us, the fast Fourier transform, which is whenever you're asking a computer to do the Fourier transform using the fast Fourier transform. The equation for that in Mathematica the syntax is printed up there on the screen. Basically, if you apply the Fourier transform to a sound wave, or to any function for that matter, but for our purposes, a sound wave, it's going to give you back a real long string of complex numbers. You can then take all those complex numbers and plot them on the imaginary plane parametrically, and you get these really, really interesting looking spiral graphs. What we're looking for is the average of all of these points on these spiral graphs. If you look at the graph on the left here, all those points average to 0. But if you look at the graph on the right, then all those points are going to average to somewhere around 0.75. The difference in these is how we can derive how much of each frequency is in a certain sound wave, a certain sine wave. So if we apply the Fourier transform to, say, someone playing middle C on a piano, it's going to tell us that, well, the fundamental frequency of that note is a C, it is a C, but all of the other harmonics, all the other frequencies that are floating around in there let us know that specifically it's a C being played on a piano. If we were to play the same note on a guitar, it would say, well, yes, this is the same note. Its fundamental frequency is the same, but these harmonics are different. These are the harmonics of a guitar. And there's a little bit more realistic code demo here. So I'll go ahead and share this piece of Mathematica code. So this is a wave that you might see out in the real world somewhere. This here is a square wave at 100 hertz. It's a 100 hertz square wave. And the equation is there at the top of the screen. All those other sine waves, or all those other cosine waves, pardon me, are the harmonics that make it specifically a square wave. And this plot here is the plot of those complex coordinates that we get from the Fourier transform of this sound wave. This slider is adjusting the frequency that we're looking for. As you can see at this particular frequency, the graph is a little bit more complex, but all of these points are still going to average somewhere off center. And because it's somewhere off center, because it's not 0, it lets us know that that frequency is in fact present there. If we slide to a different one, say the start over here, give Mathematica a moment to render, then this is again like a large complex graph, but all the points are going to average to 0, which lets us know that the frequency that we're checking for here is not present in our sine wave at all. Then, so if we go back to, the program itself, this is what our program is doing. So here's a little bit of a simpler example. This is a triangle wave. Within this triangle wave, there's a 1 hertz, 3 hertz, 5 hertz, 7, and 9 hertz frequency. This top graph over here, where everything equals out to 0, is us checking for a 4 hertz frequency, using the fast Fourier transform to check for a 4 hertz frequency. all of these points are going to average to 0. And the equation corroborates that. There's no 4 Hertz frequency present, which means that the amplitude of that 4 Hertz wave is 0. The bottom graph over here is a 5 Hertz wave. That's going to average, like we said before, a little around 0.75, which means that relative to all of the other waves, the amplitude of a 5 Hertz wave is 0.75. Now, we can take this just a little step further, and this is how it's going to be displayed if you're using the program. So we take the graph of all of those amplitudes and plot them over here. So the x-axis on this graph on the right is the frequency axis, and the y-axis is the amplitude axis. If you look at the equation that's on the screen now, this is another square wave. We have 10, 30, 50, 70, and 90 Hertz waves in here. This is what the fast Fourier transform tells us as well. Down here at around 10 Hertz, there's a very, very large spike, amplitude of 200, which lets us know, oh, that's the fundamental frequency of this wave. And all of these little harmonics over to the side tell us that not only is this a 10 Hertz wave, but this is a 10 Hertz square wave specifically. Our program then takes that information, says, oh, we know all of this. We can turn it back into a regular, we can turn it back into a analog synthesizer preset. If you look at this graph, this is a graph of an actual sound wave. I believe this is a recording of me saying the word hello. But for those vowel sounds, the E and O and hello, they are going to show up over here on the left of the fast Fourier transform as large spikes. Those are the pitches that my voice was at whenever I said those words. And then all of the other frequencies are the harmonics to let you know that it was my voice, to let you know specifically I'm saying the word hello. And then it's also everything else, like the air conditioner running in the background, the microphone that I'm using introduces certain harmonics. That's all data that's present within this specific wave. So we're going to go ahead and demo the actual program now. Oh, hold on, stop sharing and go back to this right here. So whenever you start the program, this is the screen that you're going to be greeting with. There's a couple little buttons up here. This is just a basic instructions button. It tells you everything that I'm telling you all right now, just how to use it, a little bit of information about how sound synthesis works. For fun on this program, we also changed the appearances. You can use whatever color scheme you would like. But to go ahead and get into the actual code itself, this is a recording that I made right before we started the presentation of me playing guitar. So I went over here, clicked the record button. That's the function being displayed up there. If you'll notice, there's a fair bit of silence up here at the beginning of the recording, and that's not useful. We don't want to have that latency. So I was able to take this slider here, this start slider, and move it up to where the sound starts. So I click the play button over here, and immediately we get this lovely little guitar chord coming back. Is the sound coming through? Okay, excellent. If we click on About, this is going to give us the Fourier transform of that audio. So because it's a clean guitar sound, we have these nice, very clear points here that tell us, oh, these are the fundamental frequencies or the specific notes that we're playing. And then all the harmonics cascade up and forwards, telling us specifically it's my guitar being played, what chord is being played, all of that information. If we move on to the play screen, it doesn't look exactly like the one that was in the presentation. Mathematica has come out with an update since we performed this, since we initially made the presentation. But everything else, all the sound functions do still work the same. Over here is the lo-fi or approximate mode, or we can use it in perfect mode. And that's going to determine which specific sample is coming through whenever we press a key. So now if I press this C key, it should give us our original sample back. And it does. If I press another key, it should play that repitched. So now I recorded the guitar sample one time, and the guitar it's up in my room, it's put away, but I can still use that guitar sound as an instrument now. I can make whatever chord progression I would like using this sampler. If I go to the lo-fi mode, it's going to take away those harmonics and just focus on the the fundamental frequencies. So it's just going to use sine waves. But the trade-off for that is that because I'm using an analog synthesizer, I'm not using sampling anymore, I don't have that issue of shortening whenever I play higher notes. Whenever I play higher notes, they're still going to sound the exact same length that I played before. But there's a lovely little sine wave code there. It's not as bright, but it's the same wave that we were making before. So that is pretty much all of the functionality that is within this program as of right now. And I would be happy to take any questions that anyone has.
Do you upload mixes of well-known pieces with this? I see them on YouTube all the time. Things like Viva La Vida is done 1,000 different ways and things like that.
I personally have not made any covers of songs, and I haven't made any covers of songs using this program specifically. But if that is something that you wanted to do, then that is something that you could do. Unfortunately, Mathematica's sound it's a little, not all of the functions work whenever you try and apply them to sound. So code importing and exporting files doesn't work consistently. So you'd have to use an external program to record the audio that's coming out of the synthesizer. So it would be better used live than it would for uploading something to YouTube. But if you had an external program like that, then yes, that would be something that you could do.
What other questions do people have?
I don't have to mute.
I want to apologize. I noticed that the recording was paused after about the few minutes of your speech, so I hit it real quickly, but I might have missed the first few seconds in the recording. So
Oh, it's no trouble. Thank you very much.
it's kind of funny. I want to talk about making recordings, and I messed up the recording. So any other questions for the speaker? We've got a little time.
Am I good? Okay, I have a question. So when you're talking about the fundamental frequencies part, where it kind of like isolates, like I guess like the core sounds like without the background noise, and am I right about that? Is that what the fundamental frequency is?
Yes.
Okay. What if you're using a sample where you're like playing a guitar at the same time as someone else is playing a piano? Is it only going to focus on one of those instruments, or is it able to combine both?
So in that particular example that you gave, if someone's playing a guitar and playing a piano, it would work just like it would treat both of those sounds as if they were one sound wave. You're only ever putting one sound recording into the program, but it can distinguish between different notes and it can distinguish between chords. Whenever I was playing guitar, I played a chord, so there's multiple notes in there. And the program doesn't care if you're playing all of those notes on the same instrument or on different instruments. So I could have played, it was a D major chord, so I could have played the root and the major third on one guitar and then played the fifth on a piano. And the program would have been okay with that. It's going to get rid of the harmonics anyway. So what instrument you play it on will not affect the functionality of the code. It'll work just the same, no matter what instrument you use.
Since Dr. Kessler is here, I'll ask you, Star, is this related to wavelets?
That's like anytime that you're dealing with sound and with waves, and especially with the Fourier transform, then wavelength and amplitude and frequency is going to be something that like matters. But I don't believe that any of our calculations are wavelength dependent. Most of the calculations that we're doing are with amplitude and with frequency. The only thing that wavelength is going to affect is the length of the sample, and that's what the sample approximation is for. We make it to where that's not something that we have to worry about anymore.
I was actually saying wavelet. Wavelets.
Wavelet.
Yes.
I bet Star doesn't know what a wavelet.
I'm afraid that's math that's just a little bit above me. I misheard you. I'm terribly sorry.
Oh,
Dr. Kessler is an expert.
well, I don't know, but Fourier analysis is superior to wavelet analysis for sound files.
Okay.
Just because of the periodicity.
Mm-hmm.
And then wavelets will be probably a little better for things that don't have that periodic, like images and things like that. where you have sharp edges, and sound has a lot more of this going on.
So when you were showing the code demo, when you got to the part with like the piano on the screen, there are a lot of sliders above that. What are some of the main functions of those sliders?
Okay, so for that, I'll go ahead and I'll go ahead and go back to the program. All of these are what are going to determine the frequencies of the pardon me. Those are what are going to determine the amplitudes and the frequencies of the oscillators in the analog version. So if you're using the lo-fi mode or using the approximate mode, that's whenever the sliders become relevant. Unfortunately, this is one of the things that broke whenever Mathematica updated. So you can see that it displays the proper amplitude values. So there's 3 notes in a D major chord, and those are those are the amplitudes of those 3 notes. They're all at 0.8, but the frequencies in hertz did not appear up at the top. But if you wanted to, it's a graphical representation of those, so that you as the user can more easily read what sine waves the program is using to make your sound.
Any other questions for the speaker? Well, let's thank Star. That was an excellent talk. I think it was great.